Hello, in this paper, we propose ViP3D, end-to-end visual trajectory prediction via 3D agent queries. First, we talk about why it's meaningful to predict future trajectories from visual data. Visual data contain rich visual information for motion prediction. For example, if a pedestrian is playing with his mobile phone while crossing the road and does not notice the incoming vehicle, then the pedestrian will keep moving forward. Compared with traditional pipeline, which involves multiple non-differentiable modules, ViP3D uses 3D agent queries as the main interface of the pipeline, enabling end-to-end future trajectory prediction from raw video frame inputs. Experimental results on the nuScenes dataset show the strong vision-based prediction performance of ViP3D compared with traditional pipelines and previous end-to-end modules. In quantitative results, ViP3D makes use of the pedestrian's head pose to correctly predict that the pedestrian will stop. Hello everyone, in this paper we propose ViP3D, end-to-end visual trajectory prediction via 3D agent queries. ViP3D is the first vision-based approach to predict future trajectories of agents for autonomous driving. This work is done by Mars Lab in Tsinghua University. First, we talk about why it's meaningful to predict future trajectories from visual data. Visual data contain rich visual information for motion prediction. For example, if a pedestrian is playing with his mobile phone while crossing the road and does not notice the incoming vehicle, then the pedestrian will keep moving forward. In addition, if the right turn signal of a vehicle is flashing, it indicates that the vehicle is going to change lines or turn right. Another key point is that why we use end-to-end learning. The end-to-end learning is helpful in avoiding the error accumulation and data distribution shift. The traditional pipeline contains multiple non-differentiable modules. Different from the traditional pipeline, ViP3D uses 3D agent queries as the main interface of the pipeline, so it's a fully differentiable end-to-end pipeline. Previous end-to-end prediction methods, such as FAF and PMP-NET, are both LiDAR-based trajectory prediction methods. Though this end-to-end method suffers from a couple of limitations. First, they are not able to leverage abundant fine-grained visual information from cameras. Second, these modules use convolutional feature maps as their intermediate representations within and across frames. So they suffer from non-differentiable operations, such as non-maximum suppression in object detection and object association in multiple object tracking. Fiery is also an end-to-end method which predicts future BV occupancy heat maps from visual data directly. However, first, it's not modularized and non-interpretable, thus not engineering-wise friendly. Second, its output representation is not compatible with downstream modules like motion planning. Now, let's take a look at the module architecture. At each time step, we have multi-view images as input. We use a set of 3D agent queries to aggregate visual features through 3D to 2D cross-attention in order to detect agents. More concretely, the architecture we use is deter3D. The input to the model is a set of agent queries. We send them into a transformer decoder and obtain 3D boxes. The 3D boxes have physical coordinates. We make a 3D to 2D projection onto image feature maps with camera intrinsic, extrinsic parameters. Then we sample the corresponding image features, concatenate them with box positional encodings, and send them to transformer decoder to further refine the boxes. After detection, the queries further interact with HD maps and are decoded into predicted trajectories. Concretely, we use VectorNet to make trajectory predictions. Each map element is encoded and becomes a node in a GNN. The agent queries interact with them through attention and are further decoded into multiple future trajectories. Then, we move to the next time step 1. The agent queries are managed in a dynamic memory bank. We only keep the query that has detected an object at time step 0 and throw away 2 queries that are empty. At time step 1, we will complement 2 new queries in case there are new objects appearing in the new frame. The new set of queries further extract visual features and predicts corresponding trajectories. Then comes the next frame time step 2. The model works similarly. tracking old objects and detecting new objects. It's worth mentioning that ViP3D works in a concise streaming manner, with 3D agent queries initialized, updated, and discarded over time. We conduct experiments on nuScenes datasets. Both mean ADE, mean FDE, and miss rate are classical prediction metrics. And end-to-end prediction accuracy, EPA, is our proposed metric for the end-to-end setting. Quantitatively, ViP3D outperforms traditional pipeline and PMPNet. We have also conducted a lot of ablation studies. Here are the ablation results on the inputs of the trajectory prediction module. As shown in the table, first, historical trajectories are no longer necessary, since agent queries captured the information implicitly. Second, it indicates that differentiability is important for end-to-end trajectory prediction. In previous experiments, we use regression-based method for trajectory decoding. We also conduct experiments on the goal-based decoding method and the heat map-based decoding method. As shown in the table, ViP3D is compatible with these decoding methods. We find some interesting cases in visualization. In this example, the pedestrian in the blue box is turning his head and looking at our SDC, so he should be waiting for us. However, traditional methods cannot capture such fine-grained information and makes a wrong prediction of crossing the road, which is the red trajectory. ViP3D makes it correct. In another example, the left turn signal of the vehicle in the blue box is flashing, indicating that the vehicle is about to turn left. However, traditional methods cannot capture such visual information and makes a wrong prediction of going straight. In contrast, ViP3D successfully predicts the left turn. Finally, here is a video demo of ViP3D. Hope you can enjoy the demo. Thanks for your watching.